When a network problem is caused by an interface issue, it often feels especially unfair because the machine looks connected and the link light is on, yet something still fails in ways that do not match your expectations. You can reach some destinations, but not others. Small requests succeed, but large transfers stall, or everything works until you enable a second interface, and suddenly behavior becomes inconsistent. These are the cases where the physical connection is not the real story, and the problem lives in how the interface is configured to move packets and how the system chooses among multiple possible paths. In this episode, we will focus on 3 interface-related patterns that commonly create confusion: maximum transmission unit, MTU, mismatches, bonding, and the complexity of multiple links acting as one, and dual-stack surprises when a system supports both Internet Protocol version 4, IPv4, and Internet Protocol version 6, IPv6. The goal is not to memorize vendor tricks, but to build a clean mental model that lets you isolate these issues quickly by recognizing their symptom fingerprints. When you can do that, interface problems stop being mysterious and become a predictable part of troubleshooting. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good mental model begins with remembering that an interface is not just a port. It is a set of rules about how traffic is packaged, labeled, and transmitted. The interface defines addressing, encapsulation, and limits like how large a single frame can be on the local link. It also participates in decisions about which route is chosen when multiple interfaces exist and how traffic should be balanced or failed over. This is why an interface can appear up while the network experience still feels broken. The interface may be up at the physical layer, but misaligned at a higher layer where packet size, path selection, or protocol preference matters. Beginners often stop troubleshooting as soon as they see a link is up, because up feels like success, but up only means one narrow piece of the chain is true. Interface issues live in the space between being physically connected and being reliably reachable for the types of traffic your applications actually send. Once you view the interface as a policy engine, you understand why subtle misconfigurations can create selective failures rather than total outages. Maximum transmission unit, MTU, is one of the most common causes of selective network weirdness, and it is especially confusing because it can allow many small interactions to succeed while causing larger ones to fail. MTU is the largest packet size that an interface can send without fragmentation on that link. In practice, networks often have a common default size, but real environments introduce variation through tunnels, virtual networks, overlays, and special link types. If your system believes it can send packets larger than what a path actually supports, the oversized packets may be dropped or may trigger fragmentation behavior that does not work correctly. This can lead to symptoms like being able to connect but not being able to transfer data reliably, or being able to reach some services but having strange timeouts when responses are large. Beginners sometimes interpret this as the server being slow or as a firewall issue, because the failure looks like a timeout, but the underlying cause is that packets are being lost due to size constraints. The key insight is that MTU mismatch failures often correlate with payload size rather than with destination identity. To make sense of MTU mismatches, it helps to understand the role of fragmentation and path discovery at a high level. When a packet is larger than what a link supports, it might be fragmented into smaller pieces, or it might be rejected depending on settings and path behavior. Modern networks often rely on a concept called path MTU discovery, where systems learn the largest usable packet size along a path so they can avoid sending packets that will be dropped. If that discovery process is blocked or broken, a sender may keep transmitting packets that are too large, resulting in repeated loss. This is why MTU problems can appear only on certain paths, such as traffic that goes through a tunnel, while local traffic works fine. It is also why the problem can appear only for certain applications that send larger payloads, while simpler checks appear normal. The beginner-friendly takeaway is that connectivity is not just about whether packets can travel, but whether packets of the sizes you need can travel. When you keep size in mind, You gain a powerful lens for interpreting selective stalls and partial failures. Bonding is another interface topic that produces surprising behavior because it involves combining multiple physical interfaces into one logical interface for redundancy or performance. The promise of bonding is appealing. If one link fails, the other keeps you up, and you might gain throughput by using both. The complexity comes from the fact that bonding behavior depends on mode, and mode determines how traffic is distributed and how failover happens. Even without diving into configuration, you can understand the core idea. Bonding changes how the system presents its identity to the network and how it chooses which physical link carries each packet. That introduces opportunities for mismatch between what the host thinks it is doing and what the switch or upstream network expects. If bonding is misaligned, you can see symptoms like intermittent packet loss, uneven performance, or connectivity that works for a while and then degrades. Beginners sometimes suspect the network is unreliable, but the real issue is that the bond is making link selection decisions that are inconsistent with the network's view. The triage skill is recognizing that the presence of bonding increases the likelihood that a seemingly random issue is actually a deterministic selection or negotiation problem. A particularly important bonding concept is that some bonding modes require coordination with the network device, because both sides need to agree on how traffic will be balanced and how the logical link is represented. When coordination is missing or mismatched, one side may distribute traffic in a way the other side does not handle consistently, leading to drops that look intermittent. Another concept is that bonding can mask underlying link quality issues, because one link might be clean while the other is degraded, and the bond distributes traffic across both, causing overall experience to become flaky. This is why bonding issues often present as partial failures rather than total loss. Some flows happen to land on the good link and succeed, while others land on the bad link and fail. For beginners, the key mindset is to treat bonding like a layer that can create variability by design. You do not immediately assume the network is chaotic. You ask whether the host is intentionally distributing traffic and whether one of the underlying paths might be unreliable or misaligned. That question alone can save you from chasing unrelated application-level symptoms. Bonding also interacts with routing and interface selection, especially on hosts that have multiple interfaces and multiple potential paths. A host might have a bonded interface for production traffic and a separate interface for management, or it might have multiple networks with different priorities. If metrics or priorities are wrong, the system might send traffic out the wrong interface, creating failures that look like routing problems even though routes exist. This is why interface issues can masquerade as routing issues. The difference is that routing tables might look correct in concept, but the interface attached to a route might not behave as expected due to bonding mode, link state, or negotiation. A COM triage approach considers whether the failure began after adding an interface, changing a bond, or moving the host into a new environment. Changes that affect interface topology are high-value clues. Beginners often focus on the destination, but in these cases the source's interface decision is the key variable. When you recognize that, you can isolate whether the host is choosing a path you did not intend. Now let's talk about dual-stack surprises, because supporting both IPv4 and IPv6 can create unexpected behavior even when both protocols are technically working. Dual stack means the host can communicate using both addressing families, and many modern systems prefer IPv6 when it is available, falling back to IPv4 when it is not. This preference can surprise beginners because they think they are using IPv4, but the system might be using IPv6 under the hood. If IPv6 is partially misconfigured, blocked, or routed differently, the host might attempt IPv6 connections first and experience delays or failures before falling back, making the network feel slow or inconsistent. This can also cause selective reachability, where some destinations work fine because their IPv6 path is healthy, while others fail because their IPv6 path is broken even though their IPv4 path would work. The result feels like randomness, but it is actually a protocol selection decision that differs per destination and per name resolution result. The triage mindset is to ask which protocol family is being attempted and whether both are equally healthy. Dual stack also introduces complexity in name resolution because a single host name can resolve to both IPv4 and IPv6 addresses. If the system receives both, it may choose one based on policy, perceived reachability, and preference. When one family is broken, the user experience can degrade in subtle ways. For example, an application might appear to hang briefly while trying IPv6, then succeed on IPv4, leading to slow page loads that come and go. Beginners sometimes blame the remote service, but the problem can be local protocol selection. Another twist is that firewall policies may differ between IPv4 and IPv6, meaning a service might be reachable over one family and blocked over the other. This can make a system appear inconsistently reachable depending on which address family the client chooses. The core lesson is that dual stack is not just two networks. It is two parallel universes of policy, routing, and filtering that must both be correct for the experience to feel smooth. When only one universe is healthy, the system can behave in surprising ways. An important commonality across MTU mismatch, bonding issues, and dual stack surprises is that they often create partial failure patterns rather than total outages. Partial failures are harder for beginners because they defy simple binary thinking like up or down. That is why symptom fingerprinting is so valuable. MTU mismatch often correlates with payload size, where small interactions work and large ones stall. Bonding issues often correlate with flow distribution, where some connections succeed consistently and others fail unpredictably depending on which underlying link carries them. Dual stack issues often correlate with address family selection, where delays or failures appear when the system chooses the unhealthy protocol family first. In all three, the machine can appear connected, but the quality of connectivity varies based on conditions that are not obvious unless you know to look for them. The skill is to observe what conditions trigger failure, because those conditions point directly to the category. Once you recognize the category, you stop running generic tests and start verifying the specific assumption that is likely wrong. It is also worth remembering that these interface issues often show up after change, because change alters assumptions about packet size, link topology, or protocol availability. A new tunnel can reduce effective MTU. A new bond configuration can change how traffic is hashed across links. Enabling IPv6 can cause the system to prefer a path that has not been fully routed or allowed through security policies. Beginners sometimes view change as a blame object, but in troubleshooting, change is a clue that points to what assumption might have been invalidated. If the problem started right after a migration into a virtual network, MTU mismatch becomes more likely. If it started after adding redundancy links, bonding becomes more likely. If it started after enabling IPv6 or changing DNS records, dual stack behavior becomes more likely. This is not about assuming causation without evidence. It is about using the timeline to choose the most productive hypothesis first. That is what best next step thinking looks like in operations. As we conclude, the goal is for you to be able to hear a description of a flaky network issue and quickly decide whether the interface layer deserves special attention. Maximum transmission unit, MTU, mismatch tends to create size-dependent failures, where basic connectivity appears normal, but larger transfers stall or timeout due to packets that are too large for some part of the path. Bonding creates a logical interface out of multiple physical links, and misalignment in mode, coordination, or link quality can create intermittent behavior where some flows succeed and others fail, depending on how traffic is distributed. Dual stack surprises occur when a host uses both IPv4 and IPv6 and prefers one family, causing delays or failures when one family is partially broken or filtered differently. The unifying triage strategy is to look for partial failure patterns and ask what condition changes between success and failure, because that condition often reveals whether the problem is packet size, link distribution, or protocol family. When you develop that skill, you can isolate interface issues quickly and communicate clearly about what is likely happening, which is exactly the kind of layered reasoning Linux Plus expects you to build.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.